Good afternoon and welcome back to our AP Physics 1 review sessions. My name is Joshua Beck. I'm coming to you from Clayton, North Carolina, and today we will be talking about simple harmonic motion. We are going to review some of the fundamentals. We'll talk about how that relates to forces. We'll also talk about how that relates to energy. We'll draw some graphs. If we've got some time, we'll look at this period of oscillation and then wrap up with some AP style questions. So hopefully you guys enjoyed Greg's lessons the past 2 days about energy. We're going to be using a little bit of that information today. So if you worked on yesterday's homework problem, just keep that close by. We'll get to that probably about at the midway point. Okay, so to begin, what does simple harmonic motion look like? We'll use some similar terms that might show up when talking about waves, but simple harmonic motion is not a wave. It's an actual object that's moving between two locations. Now, it's an oscillation, so it cycles through and it kind of repeats this motion. So it has some of the same terminologies as a wave. It'll have an amplitude. It's going to have a maximum displacement on one side or the other. It'll have a frequency, which will be the number of oscillations per second. It'll have a period. That's going to be the time for each individual oscillation. So we've got some of these same terms, but keep in mind, simple harmonic motion is talking about an individual object that's moving back and forth. So like a mass attached to a spring as it oscillates. So even though there's some similar terminology, I know some people were asking us, I thought waves weren't on the test. Well, these aren't waves. This is just describing the motion of an object. And because it's cyclical, it has some of these similar terminologies. Now, if we were to look at the displacement of an object as it went up and down right here, we could look at this graph and see that the period is 2 seconds. We could find the frequency, taking 1/2, the frequency would be 1/2, and we could actually create an equation to describe the motion of this particular object. This is not exactly where I want to focus my energy today. Where I want to focus our time is actually on the various points throughout simple harmonic motion. So in order to create this motion, what we need to do is we need to apply a force that is in the opposite direction of the displacement. So if something moves one way, we need to have a force that's going to be a restoring force that's trying to push it back the other way. If it does go back the other way, we need to have a restoring force that pushes it back towards its original placement. So we need a net force that's going to be in the opposite direction of our displacement. We also need that net force to be proportional to the displacement. So the further it gets from an equilibrium position, we need that force to get bigger and bigger and bigger. So it's going to increase with displacement. So we take an object, it's got an equilibrium position, we move it to the right, and we need a small force to the left. We move it further to the right, we need a bigger force to the left. If we move it to the left, then we need a small force to the right. If we move it further to the left, we need a bigger force to the right. So the examples in P1 that would create this type of motion would be a mass attached to a spring. Obviously, the further we stretch that spring, the larger the force is going to be, and it's always going to be a restoring force. And then a simple pendulum. The actual calculation of where that net force comes from is a little bit tricky, but just understand that the further you pull a pendulum back, it's going to be a larger net force that's pulling it back towards its regular position. Today, we're going to focus primarily on mass spring oscillators. So here we've got a setup. You've got a mass that's in an equilibrium position. Now I can move this to the right, and I've got A labeled as the positive amplitude. That's the largest displacement. I'm going to give this to the right. And then we've got negative A labeled as our amplitude on the negative side. So the first question I want to ask you today is, where would you expect to find the maximum force? So the force that's going to be applied to this object M, where would we expect to see the maximum force? Well, remember that this force is being generated by displacing this. So when we're in the center here, this hasn't been displaced at all, so we don't have any force. As we move it to the right, the force is going to get larger and larger and larger until we end up over here. We should end up with a maximum force. Now, the same thing is going to occur on the other side. As we move further and further and further, the force gets bigger and bigger and bigger. And we should have a maximum force here. Now, keep in mind, forces are vectors, so the direction matters. And the direction matters if we're trying to create simple harmonic motion as well. We need that force to be opposite the displacement. So if I've moved this to the x side, the positive x side, I need to have a negative force. This force is actually going to be aimed this way. If I've moved it to the negative x side, so that negative displacement, then this will be a positive force. That'll be this way. Now, how could we actually calculate this maximum force? Well, this is a spring that's stretching. So the force of that spring will be calculated with Kx. Whatever X max is, that's going to give us our maximum force. All right, and that could be a positive, could be negative, but this absolute value, the size of this force is going to be K times whatever that displacement is. Now, is that the force at all points? So if it's on the right, does it experience that maximum force the whole time? And a lot of times people look at springs and they calculate, all right, at a maximum displacement, this is the force from the spring. And so then they just assume, all right, well, I've got that same force the whole time. But that's not the case, because when we're in the center, there's no displacement. So the force is actually going to be 0 in the center. So we have F equals 0 right here. We've got a maximum force on one side, maximum force on the other, and it's going to increase the further and further we go. Okay. Now we're going to look at some examples today. In order to do this, I'm going to see if I can switch around. I can switch this video. Sorry about this. I'm trying to go fast. Switching this video. If you look, the video that did have my face on it is now over here. It's my little lab setup, and I've got this spring with a certain mass attached to it. If I move this thing will start to oscillate like this. Now, you may be wondering, well, wait a minute. This is a horizontal spring, or this is a vertical spring. You were just looking at horizontal springs. So what gives? Well, without going too far into it, basically, if you have a horizontal spring and you displace it, then the net force is going to be Kx. If you have a vertical spring and you start from the equilibrium position, then the net force is still going to be Kx. Easiest way to think about this is when it's at the bottom, you have stretched this an extra distance, so the spring is stretched an extra distance, so that extra force is going to be Kx. When it's at the top, well, that spring isn't stretched quite as far. So now all of a sudden, that force of the spring and the force of gravity are no longer balanced. So the force of the spring is smaller, so that net force is due to that decrease in that force of the spring. Well, how much did the force of that spring decrease? Kx. So whether you're above or whether you're below, the net force is going to be equal to Kx as long as you start from the equilibrium position. Same thing applies if you're on an inclined plane. All right, the forces are coming from the spring, and they're also coming from that mg sine theta component, but the net force will always be equal to Kx as long as you measure x from the equilibrium position. Now you can take my word for it, or I've got a little video here where I have two springs that are the same. They have the same K value. They both have the same mass attached to them. It's 500 gram mass and a 500 gram cart. And you can see that they oscillate with the same amplitude and with the same period because I displaced them both the same amount to begin with. Now, if I started this problem at the original length of the spring, then all of that goes out the window. So we need to start with this at its equilibrium position. So what I'm going to do today is I'm going to switch over so you can actually see this data collection. And here I've got a motion detector at the bottom. And then at the top of this, I've got a force sensor way up there. Where is it? There it is, my force sensor. Okay. So what I've already done is I've already zeroed this force sensor and the motion detector. It may have moved around a little bit, so I'm just going to do this one more time. I'm going to zero both of these. So what I'm doing is I'm now calling my equilibrium position 0. So if I pull down on this, you'll see that there's going to be a net force of 0.8 newtons. If I push up on this, we've got a net force of negative 0.8 newtons. Okay, so I've zeroed it at this equilibrium position. So I'm just going to let this thing go, and we'll collect some data here. This is what simple harmonic motion will look like. This position will follow this cosine curve or sine curve. They look exactly the same, just different starting points. So it's going to follow this curved pattern. Now, what I want to look at is to see where we actually find our maximum force. Let's see if I can notate here. If we look, this is our maximum force. So this is F max right there. Well, where does that come into play? Where does that line up with the displacement of this? If I look at this maximum force, you can see that this occurs when I was at negative A. When my displacement was at its maximum negative displacement. Now you can see I have another maximum force here. This is my negative maximum, and you can see that that occurs where positive A was, just like we drew on the diagram. Now when I'm at the equilibrium position right here, this is my equilibrium position, you can see that my force equals 0. Now I want to ask you a question about this. What do you think would occur, or how would this be different or similar? What would it look like if we were trying to identify the location of our maximum acceleration? I'm going to get my video back up here so you can actually see me. I'm still here. Don't worry. Didn't go anywhere. So where would our maximum acceleration occur? We've got our equilibrium position. We've got positive A. We've got negative A. Where would our acceleration occur? Well, I'm going to take this graph and I'm just going to change the y-axis. The nice thing is this motion detector and this force sensor together gives me a really robust data set that I can choose from. So I'm just going to simply switch this. I'll leave the notation, change this to acceleration. And if you look, I actually end up with my maximum acceleration at the same point as my maximum force, the same point in time. And then I see my negative maximum acceleration at the same place with my negative maximum force. And then where force equaled 0, I have an acceleration of 0. Now, hopefully that makes sense, because what is it that's actually causing this acceleration? What is it that's actually causing our acceleration? Our acceleration is caused by the net force. So if our net force was at a maximum here and here, then we would expect to have our acceleration at a maximum there and there. Now this was a negative force, so it'll be my negative acceleration, this is positive force. That's just defining the direction. It means the acceleration is to the left over here, and the acceleration is to the right over here. Now, how could we calculate that? Well, acceleration is calculated with just the net force divided by the mass. So our net force was kx max. That was our maximum displacement, so that's our maximum force. So that would give us our maximum acceleration. Now, where would you expect to find an acceleration of 0? Well, right in the middle, where there's no displacement, so that there's no net force. So here we'd find our acceleration of 0, just like the graph showed us. All right, let's look at some other kinematics variables. As this thing oscillates back and forth, where would we expect to find the maximum velocity? See, on the outside here, this is where we found our maximum forces and our maximum accelerations. But is that where it's going the fastest? No, because if it had any velocity there, then it wouldn't be at the end. It would still be moving. This is actually going to be a point where we have our velocity of 0 at these edges, which means that our V max will be here. At one point, it'll be going that way, and at the other point, it'll be going that way. But that'll be our maximum speed right there. Now, how could we calculate that V max? Some of you are going to look at your kinematics equations, and you're going to start to try and find one. You're going to say, all right, V squared equals V initial squared plus 2A delta X. Perfect. I've got delta X. I could find some A values, this and that. But I'm going to stop you right there. Greg mentioned this yesterday, and I want to make sure to reiterate it today. Why can't you use kinematics here? Well, these kinematics equations are based on a specific acceleration, a constant acceleration. Is our acceleration constant throughout this range of motion? Well, is our force constant throughout this range of motion? No, if our force is varying, then that means our acceleration is varying. So I can't just plug in a single value here. So how could I figure out this maximum velocity? Well, I'd have to take an energy route. I'd have to look at how much potential energy is stored in the spring when it's compressed all the way. And then that will turn into kinetic energy. So if I take X max, cancel this, divided by M, this will give me V squared. So I could solve for my maximum velocity this way. Now, where would I expect to find velocity of 0? Well, that would be on the outside edges. All right, let's continue to analyze this motion, and let's see where we expect to find the maximum kinetic energy. Well, kinetic energy is going to be based on the velocity. So wherever we found the maximum velocity, that's where we would also find the maximum kinetic energy. Okay, how could we calculate it? Well, once we knew the maximum velocity, we can just plug it into this equation here. Are there any points where we would find a kinetic energy of 0? Well, sure. When it's out here, the velocity is 0, so that means that k is going to be 0. And when it's here, the velocity is 0, so k equals 0. All right, one final variable to look at is what about potential energy? Well, potential energy is based on the displacement of different parts of our system. Well, if it's in our equilibrium position, it's not displaced. Once I displace it, the further and further I displace it, the more and more potential energy we're going to get. So I'm going to have my maximum energy here, and I'll have 0 energy there. How could I calculate this maximum energy? Well, if my net force is calculated with kx, then my potential energy will be 1/2 kx squared. Now, again, I don't want to get too far into it. Even if this is a vertically oscillating spring, as long as I measure x from the equilibrium position, then my potential energy at any given point will also be 1/2 kx squared. Now, I know some of that potential energy is coming from the spring, some of it's coming from gravity. As far as figuring out the combination, how much is from each, that is not a question for P1. Okay, what we do need to know is that if you measure from that equilibrium position, whether it's a horizontal oscillating spring, vertical, or anywhere in between, as long as you measure x from the equilibrium position, then the net force will be equal to kx, and the potential energy will be equal to 1/2 kx squared. Okay, and where would we find potential energy is 0? Well, that would be where there's no displacement, so that's going to be your equilibrium position. Now, how could I find the total energy? Well, the total mechanical energy in this particular spring oscillator is just going to be the combination of the potential at one point and the kinetic at that same point. Now, here's the question from yesterday. This is the homework problem that Greg left you with. Okay, there's a bunch of information in here with masses and speeds, things like that. That was necessary for various parts of the problem where you were calculating different values. But what we're looking at here is we're looking for the shape of this graph. We're trying to sketch a kinetic energy versus position graph. Okay, so I'm going to start by looking at this energy one, then we'll come back to the acceleration one. Now remember, this is not as a function of time. This is as a function of position. So our position axis is constrained. We've got our maximum displacement on the positive side, our maximum displacement on the negative side, and then we've got 0 in the middle. Okay, so how could we graph this? Well, kinetic energy. First, let's talk about where its value is 0 and where its value is maximized. The kinetic energy will be maximized when it's moving the fastest. So that's going to be as it passes through that equilibrium point. So I'm actually going to label this right here. This is going to be K max. Now, when the velocity is 0, which will be at the ends, then the kinetic energy will be 0. So now I've got 3 points. I need to connect them. All right. So do I connect them like this? Connect them like this? Do I connect them like this? Which way do I do this? Well, let's think about it. Let's think about when we first displaced just a little bit. These are pretty small forces, which means we have pretty small accelerations, which means delta V is going to be pretty small right here. So from that location to that location, I'm going to have a small change in velocity. So I'm going to have a small change in kinetic energy. Now, once I get over here, these forces get a little bit bigger. So the accelerations get a little bigger. So the delta V's will be a little bit bigger. Once I'm all the way over here, these are our maximum forces, our maximum accelerations. So these are going to be creating the biggest change in V. So what we're going to experience is we're going to see a small drop off here in the beginning. It's going to get bigger and bigger. Small drop off, and then it's going to get bigger and bigger. So this should give us the shape of our kinetic energy graph. Okay, now in order to kind of check this, I'm going to go back to graphs we just made. Here we've got position, and this time as a function of velocity. So this was oscillating up and down, position as a function of velocity. So you can see, I'll just kind of highlight here. You can see that when it's at a maximum position right here, you can see that the velocity is 0. That's what we would expect to see. Now, when it's in the equilibrium point, so our position graph is at a value of 0, you can see that my velocity is maximized. Now, that's a negative velocity. Keep in mind that when I calculate kinetic energy, that's going to be squared. So I'm still going to end up with a positive kinetic energy. Energy is scalar. There's no negative kinetic energy. It's going to be positive regardless of what the direction of our velocity was. So I'm going to take this graph down here, and I'm actually going to populate it with our kinetic energy as a function of time. So you can see that down here, when our velocity was at a negative max, that's still going to give us a positive kinetic energy, but a maximum value. Once our velocity reached a peak over here, that's the positive max, that's where we get our positive kinetic energy. And then we end up with, when the velocity is 0, which is at our maximum displacement, that's when we have a kinetic energy of 0. Now, this doesn't look like my graph. Well, that's okay. The graph that I drew was kinetic energy as a function of displacement, not as a function of time. So I'm going to make this graph a little bigger, and I'm going to change the axes here. Our displacement is supposed to be on our x-axis. So I'm going to put position here. Now we don't see anything because I don't have it scaled appropriately. So let's go ahead and set the maximum displacement that I had was negative 0.04 on one side and positive 0.04 meters on the other side. So this is the graph that we just drew. Look at the y-axis here. Excuse me, the x-axis here is now position. So we get this nice curve path. Now there's a lot of variation here. It's collecting it from a bunch of little data points, but we can definitely see that this is absolutely the shape of our graph right here. Now that was the first part of that homework problem. I'm going to go ahead and take this a step further before I answer the second part. What about the total energy? Well, if I look at the mass, the spring, and the earth as a system, then all the forces involved are internal forces. And if the internal forces are the only forces acting on this, then the change in energy is going to be 0. So right here, this is my maximum kinetic energy. That represents my maximum total energy. So my total energy is actually going to be up here like this. Now you can see that as it gets further away from that equilibrium position, once it gets closer to that maximum displacement, that maximum amplitude there, you can see that the kinetic energy drops to 0 because it stops moving. But that energy has to still exist. So it exists in the form of potential energy. So we would expect to see at that point, here we're going to see our max potential energy. Same thing over here, we see our max potential energy. And in the middle, we'd get U equals 0. So I can see that this is 1 point, this is 1 point, this is 1 point for my potential energy. Now, how can I connect them? Here's a helpful little hint. I know that when my energy is split 50-50, half of it's going to be kinetic energy, half of it's going to be potential. I've already drawn my kinetic energy graph. So here's my 50-50 line. That's 50%. So now I actually know that when I have that much kinetic energy, the other half of it's potential energy. So they're both going to cross this point. That's going to be the 50-50 line. So this will actually be curved like this. Now that should make sense. If our potential energy is graphed this way, that's 1/2 kx squared, so it should be parabolic. Now let's look at the second part of our problem from yesterday. The second part was looking at acceleration as a function of displacement. So let's start at the equilibrium position. We've already talked about what the value should be. What is my net force when I'm in the equilibrium position? It's 0, right? So what should my net acceleration be? Remember, my acceleration is going to be the net force divided by m. So if my net force is 0 when it's in the equilibrium position, that doesn't mean that there are no forces. It just means the net force is 0. Well, that means my acceleration should be 0. How about when I move to the right, when I move into that positive side? Well, my force gets bigger and bigger and bigger, so my acceleration should get bigger and bigger and bigger. Does that mean I'm up here? Well, no, not exactly. Because remember, if I'm moving towards the positive side, then I need to have a restoring force. My force is actually to the left, so my force is actually in that negative direction, which means my acceleration is in that negative direction. So my maximum negative acceleration would be here, and my maximum positive acceleration would be here. And we end up with, well, if I could draw these in the right spot, we'll try this again. There we go. We get a line that looks more like this. Now here's a straight line. So I'm curious, if this is a straight line, is there any significance to the slope of this? Well, let's look at our acceleration. It's net force divided by mass. So my net force, remember, is determined with just kx divided by m. Well, if you looked at x is my horizontal axis. So if this is my y-axis, that's my x-axis over here. I kind of missed. This is my x-axis over here. So that means that this is the slope. So the slope of my graph should actually be equal to k over m, okay? So let's take a look. Let's see what we can come up with. Going to go back to our little camera here. This is going to give you a picture of our setup again. Hopefully you guys can see that over on the side. And I'm going to switch the main screen back to our data collection. Okay, so first let's see if I pull this thing down. I'm going to collect some data here. we can see that our acceleration is changing from positive to negative. It's increasing and decreasing in magnitude, and the direction's changing. Okay, let's see. But we want to create an acceleration not versus time. We want to create an acceleration versus displacement. So let's make this graph a little bigger. Let's change this to position. That'll give us our x value. We're going to go from negative to positive 0.2. All right, so this should be the graph that we're trying to create. This is the second part of the homework problem. So I'm gonna go ahead and let this thing get going, and then we'll collect some data. And sure enough, I just rescaled it. There we go. And we get this slope right here. Okay, so we get this graph that looks like what we'd expect to see. I'm gonna highlight this section here. Let's find the slope, and it says here that the slope is going to be negative 0.44. Excuse me, negative 44. Slope is negative 44. Okay, go ahead and stop this. Okay, so negative 44. Let's go back to our graph that we drew. Slope was negative 44. Now, what's the significance of that slope? We said it's K over M. Well, this spring, this blue spring, has a K value of 20 newtons per meter. Okay. The mass that I have attached to it right here is a 200 gram mass. This is a 200 gram mass. And then this over here accounts for about 50 grams. It's all this duct tape in the paper here. So the mass that I've got on here is about 0.5 kilograms. So if I were to take K over M, in this particular case, 20 divided by 0.45, we end up with a slope, or the value of 44, which is almost dead on what we had from our slope of our line. So that's good. All right, so we've got our shape that matches and our slope matches. All right, let's look at some practice problems here. Well, as this thing oscillates, it's going to have a certain period. Period is going to be the time that it takes for it to go from one point all the way through the full cycle and then back to that point. So that could be from the peak all the way to the peak again, could be from the lowest point all the way to the lowest point again, or from that equilibrium down through equilibrium and then back. Okay, so through the full cycle. The time that takes, you've got an equation for that on your equation sheet. It's 2 pi times the square root of m over k. Now, if you have a pendulum, we haven't looked at pendulums today, but they also oscillate with simple harmonic motion for a simple pendulum at small angles here. And that would be determined by 2 pi square root L over G, L being the length of that pendulum and G being the Earth's gravitational field. So if you have these equations, you can certainly do some proportional reasoning. You've had a lot of practice with factor of change, proportional reasoning. How can I find how one value will affect the overall value, or if I double something or triple something, what does that do to the other value? So I'm going to leave this problem up here. This is a example where I've got a blue spring constant printed, the green spring constant is printed. I've got 400 grams or 0.4 kilograms oscillating on the blue spring. You can see I'm hiding the mass on the green spring. But you can see that as these things oscillate, they're going to oscillate with the same period. So if you want to give yourself an extra little challenge, go ahead and see if you can calculate what this particular mass would have to be on the green spring in order for these to oscillate with the same period. All right, so I'll let you take a screenshot of that. If you want to try that problem, send me a picture of your work on Twitter, and I will be sure to help you with any questions on that. That's not the homework per se, but that's just an extra little problem. We've had so much practice with proportional reasoning over the last few weeks. I don't want to spend a lot of time there. Instead, I want to give you a scenario where simple harmonic motion might kind of sneak its way into a problem. Last week, I talked about projectiles, and I showed you how projectiles can kind of be snuck into various types of problems. I want to do the same thing here. Okay, I want to show you a type of problem where you might end up having to use simple harmonic motion, even though it may not be so obvious. So here's the setup. We've got a cart, it's moving, it's got a mass of m, a velocity of v, and it's about to hit this spring. That spring is a spring constant k. When it hits this, it's going to be brought to 0. a speed of 0, and then it's going to be launched off, and you're told that it's launched with an equal speed off in the other direction. All right, so the first part of this says, using conservation of energy, derive an equation that could be used to find the maximum compressed distance of the spring. So I'm going to say that point 1 is just before these things collide. I'm going to say that point 2 is when this cart is at its maximum displacement and this thing is compressed all the way, or as far as it will compress. Okay, so before it collides, all of our energy is going to be kinetic energy. So we're going to have 1/2 mv squared. Now at point 2, I'll call this V1. At point 2, all that energy is going to be stored inside of the spring. So I'm going to call this 1/2 kx squared. Okay, so if we want to derive an expression for the maximum displacement, then that would be when all that kinetic energy has turned into potential energy. So we can do this. mv1 squared over k, that would equal x squared. So then we take the square root of that, and that would equal x. And now I haven't used simple harmonic motion yet, just a simple energy conversion. So let's continue with the problem. It says using the previous equation. Okay, so we're going to use an equation from earlier in the problem. Determine the value of the maximum force. Well, remember that the force is going to be calculated with kx. That's going to be the magnitude of the force is going to be k times the magnitude of our displacement. Well, I just solved for my maximum displacement, so I'm just going to plug that in for x. Done. That's going to be my maximum force. Now you say, well, can I cancel those k's? Well, no, you can't cancel those k's because one of them is inside of that square root. Well, could I do some algebra to get them so that I could sort of cancel something out, or could I simplify this? Sure, you could definitely jump through some algebraic hoops and it would serve you no purpose because you already have an expression. It's in terms of the variables. Leave it. You're done deriving. Okay, you don't need to simplify it down. You don't need to break it down. That's an expression. It's in terms of the given variables. You're good to go. Now calculate or determine the maximum acceleration. Well, acceleration is going to be based on our net force divided by the mass. So take that net force from the previous problem and divide it by the mass. Done. Don't need to simplify. Can't cancel those m's because one's inside that square root. Don't worry about trying to make it any simpler than it is. You have an expression. It's in terms of the given variables. Now, we still haven't used simple harmonic motion. I thought you said simple harmonic motion would come into play here. Look at part B. Determine the amount of time that passes from the moment the cart hits the spring until the moment that the spring is compressed to its maximum amount. Okay, well, I've got forces and I have accelerations, and I just came up with some equations for force and acceleration. So I'm going to go to my kinematics. I'm going to use this equation here. That's my maximum displacement. This is my initial velocity, so that's v. My acceleration, well, I just found some equation for acceleration. I'm going to stop you right there. That was the maximum acceleration. That was the acceleration at one point, because that was the force at that one point. But everything leading up to that, there was a different force, meaning a different acceleration. If your acceleration is changing, then I cannot use my constant acceleration kinematics equations. Okay, well, let me do an energy analysis. Sure, go for it. Do an energy analysis, but look at what you're trying to solve for, the amount of time. And that energy analysis, we've already used that to find the displacement. That's not going to help us find the time. This is where simple harmonic motion can come in handy. It doesn't have to be something just repeatedly oscillating back and forth, back and forth, back and forth. This is going to be a mass attached to a spring for a period of time as it goes this way and then back. Now imagine if it's stuck to the spring, then it would just oscillate back and forth. Hey, cool, we just created a simple harmonic oscillator. But we still have a portion of that. So let's look at this. It's where it's going to start. We'll call this our equilibrium position. Now it's going to go over to here. That's like our positive A. Then it's going to launch it back to here. That's back to our equilibrium position. Now just imagine if it was attached. If it was this oscillator, it would go over to here. That'd be negative A, and then it would go back. Well, that entire trip is capital T. That's the period of oscillation. So we spent a fourth of the trip going here, a fourth of the trip going here, a fourth of the trip there, and a fourth of the trip there. That gives us our full cycle. So the question says, determine the amount of time that passes from the moment it hits until the moment the spring is compressed to its maximum amount. Well, that's a quarter of an oscillation. That's a full period, but it's divided by 4. So that's going to be 1/4 of our full time, or the period, for an oscillation. Well, remember that the period of an oscillation is 2 pi square root m over k. And then we're just going to divide that by 4. Yeah, you can simplify if you want. There you go. Simple harmonic motion snuck into what looks like an energy problem. If you're looking for time, this is often a route that you can take. Now in the second trial, the cart hits the spring with a different speed. All right, so we're going to take some of these equations we just used and we're going to address this problem again from a little bit different perspective. Okay, so how would this affect the compressed distance? Well, using this equation, if I increase my velocity, that's going to increase the maximum displacement. By how much? Okay, well, I'm going to double it and then square it, so that's 4 times, but then I'm going to take the square root, so it's actually going to be 2 times. How would the time compare to part B? Well, remember the time is this period of oscillation divided by 4 because it's 1/4 of a full oscillation. It's attached to the spring. It's going to be going through a segment of simple harmonic motion, but just a quarter of it. So remember that was 2 pi. This was the previous part. We said this was 1/2 pi m over k. Well, I've just changed velocity. Is velocity in any of this equation right here? No. So how does it change it? How would the amount of time compare? It'd be exactly the same. Now, does it go further? Yes, absolutely. The cart has more energy. It's going further. Okay, there are larger forces at play. But the total time that it takes for this trip, because it's going further, yet there are larger forces, so there's greater accelerations, so bigger swings in velocity, it can still travel this greater distance in the same amount of time. Now, if the collision was inelastic, so if it's inelastic, then our velocity when we start the simple harmonic motion is going to be a little bit lower. That won't affect the time either. Would it affect the maximum displacement? Absolutely. But it won't affect the time because we're still going to have the same mass attached to the same spring. It'll oscillate with a different amplitude, but it's still going to oscillate in the same period of time. All right, in the third trial, we're going to change the cart. So now this cart has a mass of 2m. It still hits with the speed of v. So now how does this compare to your time? Well, at this point, hopefully you recognize the time is being determined based on this simple harmonic motion, because that first portion of its trip is just a quarter of an oscillation for a simple harmonic oscillator. So that time, I'm not going to continue to derive it. We ended up getting 1/2 pi m over k. Is that the period for a full oscillation? No, not at all. That's the period for a quarter of an oscillation. That's the window of time that we're looking for with this problem. It's just a quarter of that oscillation. Well, 2m means that this is now going to be 2m. So this equation here is going to be increased by the square root of 2. So whatever our initial time was, our second time will be a little bit longer. Now, why is the time going to be a little bit longer in this case? Well, it's the same spring, right? It's the same spring, except now that spring, every time it applies a force, that force is being used to accelerate a larger mass. So that same spring being compressed certain distances is going to be accelerating a larger mass. So that's going to be decreasing the acceleration, so that it's going to take longer to slow this down. Okay, and then bring it to that point of, or that point where the velocity is 0. It's going to take a little bit longer to do so. I'll give you another example problem here. Talked a little bit about how pendulums can be modeled as simple harmonic oscillators, as long as it's a simple pendulum, as long as it's a fairly small angle. So we're going to take a student, they're going to run directly up to a long rope that's attached to a tree branch. All right, the speed is entirely horizontal when he grabs a hold of the rope at point A. They'll swing up to an unlabeled point B. So somewhere up here, we're going to have another point B. Okay, same prompt, except for now, I want you to think about what could be asked. got a pendulum, we've got somebody going from one point to another. Could this question ask you for some sort of an energy analysis using the speed, height, things like that? Of course, absolutely. When you take your exam, it helps to know as you start to read the problem to start to kind of partition your knowledge and say, okay, with this type of problem, it's possible I could be asked about energy. So let me start wrapping my head around some energy stuff. Is it possible they could ask you a force analysis using the tension? As this thing travels, you've got a tension, you've got mg, maybe you're finding a net force, perhaps you've got circular motion analysis at the bottom. Sure. Could you also use a simple harmonic motion analysis? Potentially, yeah. If they're asking you about the time, because your accelerations are changing, so you can't use kinematics for this. So you could use simple harmonic motion. So here's your actual question. Go ahead and take a screenshot of this. Okay, the time from A to B, that should say back to A. I'm sorry, that's a typo. So the time for the student to go from A to B and then back to A, I've identified as T. So the question is, how would T change if the student ran faster? How would T change if the student had a greater mass? And how would T change if the student grabbed the rope higher up? Treat each of these as its own discrete change. So compared to the original, if the only thing you changed was running faster. Compared to the original, if the only thing you changed was a larger mass. And compared to the original, if the only thing you changed is grabbing the rope a little bit higher up. Okay, so treat each of these as a discrete change. And I want you to use simple harmonic motion and what you know about an oscillation and how that relates to period and time for this pendulum. And I want you to see if you can answer these 3 questions. Okay. Hopefully this is helpful for you today. If you have questions about anything I've covered, please feel free to reach out to me on Twitter. I'm going to take the next probably 30 or 40 minutes or so and keep an eye on that and be sure to answer all your questions as they come in. I'll be glad to help you as we help kind of clarify anything from this particular lesson today. If you have any questions about older lessons, feel free to reach out to me. If you want to work on this problem, I will be going over it on Monday. On Monday, we will also be going over some old, previously released free response questions. So starting next week, we'll be focusing on individual free response questions and some helpful techniques and hints, and hopefully keep you guys from falling into any misconceptions or pitfalls as you look at these different problems. So please enjoy your weekend. Please take some time, spend some time with your family, spend some time relaxing, and I will look forward to seeing you guys again. Whoop, don't need any of this. Sorry about that. And I will, sorry about this. I'm losing track. What am I doing? What am I doing? Everything's all mixed up. Sorry, here I am. Hey, live broadcast, right? I will see you guys again on Monday. So once again, please enjoy your weekend and take care. Thanks for watching.